But this is part 2 of the Unit 3. We went up to the point where it was the tank in the box, and we made a system, and we're going to take that and move beyond a little bit more into what we are going to have the basic refrigeration cycle. You've already broken down the components, and I've started to introduce to you some of the common refrigerants. So I got to pull this down. I can't breathe, so every now and then I'm just going to take a minute and just get a couple breaths of air. I'm supposed to step outside and we're not going to do all that. We're not going to get into it, but I want to show you there's a thing that you can see over here. Once we break down the system and you start to diagram it, we can plot the refrigerant cycle on something called a pressure enthalpy chart, a PE chart, that is specific for each type of refrigerant that we have out there. And on the engineering side, you can use it as a troubleshooting tool in the service side, but it's more really for the engineering side of the HVAC systems to calculate capacity and things like that. So what we're really focusing for really is these top 4. The top 4 is what I'm trying to get with you today. Because with the common refrigerants, you're also going to learn the common oils that we use with each refrigerant, which is what we sort of talked about on Friday before we left. Again, just to review how heat's transferred, what's happening here? What's going on inside the house?
Heat rises.
Heat rises, that's right. So, but they've got the heat being drawn down here low in the return, and then it's going across this component. What's inside? That's a return, but what is this component here? We got the 4 basic components. 2 are here, and 2 are here. What 2 are going to be out here? Outside.
Oh, is this
It's an air conditioning unit. So that's our condensing unit. And then I heard somebody say evaporator, so that's in here. So the metering device is probably really close to the evaporator on this side. And this is a split system. So what's going on here is the warm air is being drawn from the bottom, and then it goes across the coil where the heat gets absorbed in the evaporator, and then it makes the air feel cooler. Now the air hasn't been made cooler, it's just transferred the heat from the air into the refrigerant, and then that refrigerant gets pumped back to the outdoor unit where the air outside transfers the heat to the outdoor space. So we're just taking the air from the heat really in the air from someplace we don't want it, and we're taking it and putting it to someplace we don't care about it, outside the house. And that's really all refrigeration and air conditioning is. And as it does that, this temperature now comes out cool into the supply. So all this here is the supply. This is my supply trunk line for my ductwork. And then this is a branch line that comes off of that trunk line for that ductwork in the supply side of the unit. Can you find the return? So if that's the supply where it blows out, where am I sucking in at in this room? Take a look around.
Through the vents?
Not these vents. These are all blowing out. And if you notice, I lose about half of my airflow here. So they had to reduce the size to keep the pressure up. But where would it be sucking in at? Where's another place that you see that it could suck in? So if it's blowing out here, and my unit's on the roof somewhere, where's another spot you see an opening like that?
Oh, right there. Right there, there's no.
No, there's one here, and there's got to be another the same size about for the air to go in. So that would be like where the filter goes to, in between the two. And you might have to do that. You might have to find this stuff. You might have to find where the drain exits on the condensate, because all this stuff is collecting and drain. Aaron, I'm going to help you out. What? Right in front of you. That's a return. So when I turn the unit on, and I take a piece of paper up here, I can tell you if the unit's on or not, because what's going to happen to the paper. So I take it up here like that, and I don't know, I can't hear. Maybe I don't know the unit's on. Let me just do a quick check to see if. All right.
I think it's on.
We think it's on.
How are you going to get it back?
I got somebody that's going to get with the ladder, you know. I got guys. Don't worry. I got a guy for this. I got a guy. I got people. I got people. Ah! All right. But you get it now, right? You get it. You get it. So here, and this should be about 20-degree difference. So if I've got the AC on, and you're starting to feel warm in here, and you want to know if the unit's on, and you come over here and you turn the thermostat down to cool, and we're sucking in 75 degrees here, That means over here, if the AC's running and everything's normal, it should be blowing out about 18 degrees, 20 degrees cold. So what would that be? 75 minus 20 is
55.
55 degrees blowing out of here. Yeah, so that's supply temperature, and they call that the spread. And that's how the home inspectors check to see if the AC is working without putting any gauges or anything on it. All they do is they take a thermometer after the AC's been running for 10 or 15 minutes and put a thermometer where the supply and the return is, and if it's less than 18, there's a problem. And if it's more than 20, there's still another problem. You don't want it to be too cold either. So they can do that, and that's called the spread, the temperature difference. It's going to be something else that we're going to bring up a little bit later. But that's our delta T, they call that, the delta T. All right, so you got the outdoor unit where all the heat's rejected at the condenser, and then this probably has a compressor as well sitting in the middle of that, just like all the other units that you've seen out back. Furnace is a little different. The furnace sits in a box, so now we've got, instead of the other piece that was an air handler, because that's all it did with the evaporator coil, was move the air over the coil. This one has the coil sitting on top of a furnace, like we got over here. And if you take a look, all our AC is up here, and all this is for heat, but we're going to use the same fan motor that we use for heat for cooling. The speed of the fan's got to change a little bit. The heat that we use for the wintertime doesn't need as much fan speed as we need for the cooling in the summertime. So we're going to have a couple different speeds to our fan when we put in this fan. And what's that right there? What do we want to protect the coil from getting?
Filter.
A filter, yeah. And that's got to be changed every 6 months. So there's a job that you do when you first start out in the trade is nothing but going out to these people's houses and trying to find their filter. It's going to be close to the return, okay? And then that's what you do. You do your maintenance, you check a bunch of stuff, making sure all the electrical connections are good. There used to be a thing where you oil motors and change belts, but they're all sealed. There's beltless drive motors now. And really, it's just a matter of just checking safeties, making sure the unit's going to shut off in case anything goes wrong with the gas furnace. In fact, there was one big one. What was your thing the other day that you had to do with the furnace?
The flame sensor.
The flame sensor, man. I just saw a guy, and I started following him the other day. They made a TikTok with it. He had 20,000 likes and like 300,000 views, and he just put it up 24 hours ago because that is a big one. There's a little tiny flame sensor that keeps the unit from coming on, and the unit will fire off. And I'll show you this a little bit later, but it looks like it's just a little sensor builds up with some carbon, and it looks like the sensor doesn't read the flame, so it doesn't think that there's a flame on, and they can't have the gas valve open if there's no flame, because then the whole house would fill up with smoke. So they shut it down, and that sensor confuses the board, even though it's on and running, to make it think that it doesn't have the gas, it doesn't have flame. So they end up sanding it, cleaning it, and then it worked just fine, right? Fired right up, stayed on, customer was happy. Did you have to replace any parts? No. It's like the people call and they can't afford the $150 service call that is. So that's an easy fix. And that guy did pretty good with it. So if you had made a TikTok, boy, you could have been TikTok famous. Yeah. So this is where we left off at the end of part one. The basic illustration of the two tanks. Now, I had a tank. And it was a little different before. It was the actual R22 tank, but now we've got our semi-hermetic reciprocating compressor, my suction service valve, my discharge service valve. The tank in blue is going to be what? The low side, which is what components on the low side of the system? No, I got my two components here, compressor and metering device dividing the high and the low. What components completely on the low side of the system absorbing the heat?
Condenser.
And what components on the high side of the system rejecting the heat? Reversed. Yeah. So what you got is when you see the thermometer, we're reading the temperature with a regular thermometer like we used back there. I got you. I'm not going to hit your eye. But that means that thermometer. This means we're using the pressure temperature chart to get our temperature. So when you see that, it's temperature, but we're getting it from our chart, okay, using the PT chart. So let's take a look here. You got the outdoor air 95 degrees. That's a typical summer day. It's what all the equipment manufacturers design their systems for, 95-degree day. So if it's a little hotter, it's not going to work to the exact specs. If it's a little cooler, it'll actually work a little better. But the indoor is always generally about a 75-degree national average. All right, some people keep 68, some people keep it 72, but typically for the national average, nationwide, we're going to say 75 degrees is that typical temperature. When the pressure in the unit's running on the high side, you're going to see the gas coming out at 278 psi-G on a 95 degree day. Now remember, if this temperature goes down, what happens to this pressure? They're related, yeah, so they drop. And then if this day is hotter, I would expect to see this higher as well. So this could be up to 325 psi if you have it on a 105 degree day. It can go up. And that's not where we say 125 degrees here. Can you hold up on that? So I got 125 degrees here, but that is my temperature related to this pressure. That's not the actual temperature of the gas coming out. You felt that when you ran that unit for a while and touched this line coming out, that it could have been 165, 175 degrees, right? You can't hold on to it for too long. So the first thing the condenser has to do, it has to de-superheat that hot gas. And that was what my condenser crew told me. You said 3 things that it was going through. First thing was to get it down to the temperature of 125 degrees. So it's got to remove, right? And because the air is 95 degrees, the heat flow from warmer to cooler, that basic law of thermodynamics, the second one, is going to let this feel like 125 degrees is going to feel, 95 feels cool. 95 is cool compared to 125. So when we have a temperature difference, you're going to have that transfer of heat naturally occur. And that's what we want. And when it's the greater the temperature difference, the faster the heat transfer is going to occur until they get about equalized. And once we get it to the point where it's changing into a liquid, in this stage right here of the condenser, so this is our condensant, the change of state, changing from a vapor to a liquid, we still have a little bit of room in the condenser to cool down that 125 degree liquid, and that extra coolant on that liquid we're going to call subcoolant. So if I had 125 degrees here, and now I measure with the thermometer here at 115, what's that difference? 125 minus 115 is 10. So I've got 10 degrees of subcoolant before it feeds into the metering device, and then changes right here because now it's all blocked off. And this is fixed. So it's like if I told all you guys could leave right now, but you got to come through here. Right? Before you can't just walk out this way. You've got to come through here. So only one at a time of you are going to be able to come out. The other metering device, which I'm going to show you a little later, it can open and close automatically depending on the temperature. So sometimes if it's open like that, how many people could get out at a time?
2 of you guys or 1 of me.
2, maybe 1 of you, 2, but we can increase the numbers, right? You can increase it. That's a metering device. That's what's happening right here. So there's a restriction on this side, which is building back all the pressure up to this side because what's happening in the compressor? The pistons are pumping. It's pushing all the gas this way. So you've got it backed up here, pushing up in on this side here, and then it's spraying liquid right at this point. And that liquid now, because it's only going through a tiny little orifice, a small hole, it is 40 degrees because what happened to the pressure?
It dropped.
It drops, so the temperature drops. And this corresponds right here, 40 degrees, with this pressure of R22 refrigerant. So if I had R134A refrigerant, this could be down to 25 degrees, 0 degrees. But the pressure is going to be lower on this side. Okay? And then what's it doing? It's got about 75% liquid and about 25% flash gas, and that is going into the evaporator where it goes in as a liquid, droplets, right? Because we want it a round ball. It's got more surface area to absorb heat, and as it absorbs the heat, it boils off into a vapor, but right here it's still 40 degree vapor. So we have the exact opposite where it's subcooled air, and if I still got the warmer 75 degree air blowing over that evaporator coil of 40 degrees, we got still heat transfer taking place, warmer to cooler. That means it's going to increase to maybe another 10 degrees. What is 50 minus 40? That's right. So we got 10 degrees of superheat. Superheat happens in the last few passes of the evaporator and in the suction line going back to the compressor. Subcooling happens in the last few passes of the condenser and going into the liquid line. And that's it. That's the whole system. And this is R22, but these numbers won't exactly match with what you're doing because these numbers here are for the refrigerant R22, and you're using what? 134A. That's right. This one's green. That one is blue. Yep, no, pink is 410, and 410, all these numbers would be higher. And that was the fear for 410, because the 125-degree temperature you needed with the 410 brought this pressure up to 400 psi, 450. And that means that we're dealing with twice as much pressure. They needed to make bigger hoses. They needed to make bigger, thicker compressors, all right? Because they thought that this stuff was going to explode and be dangerous. And this happened with R22 when they used to use R12 for everything. R12 was used before 22 in all the AC systems. And then they changed to R22 because it was cheaper to manufacture and it was a hydrochlorofluorocarbon, which made it a little different on the whole way it worked compared to the CFC, the chlorofluorocarbon. Now, again, I'm going to show you. If you look in the book, this is probably more realistically the way the system's going to look. Because it's going to have, instead of the tanks, the coils, which is what I gave to you. So now you've seen this as a pretest. The compressor, the condenser, so the gas now, instead of going this way, is coming this way. Usually there's an arrow telling you, but because these are colored, you know that the gas comes out and goes into the high side, high pressure, high temperature, and that's probably going to be a red color. Our metering device is here, and I'm going to start my story here. So our evaporation comes right when the metering device changes from high to low pressure liquid, and that liquid boils off immediately and starts to flash. And then by the time we get to here, it's fully evaporated. And then that means that if it's 40 degrees here and it runs through one more pass with this 75-degree air blowing over it, I'm going to have 10 degrees of superheat. And by the time, if I got a real long run, like that run over there, it's not that long. But if I had to go to the outdoor unit where it was out back, that's going to be a real long run that we might have it going through this 75-degree room, and it's going to heat up another 10 degrees. So I've got my evaporator superheat measured right at the exit of the evaporator, and I've got my compressor superheat measured right about 6 to 12 inches away from where the suction service valve is on the compressor. All right, and that's usually going to be warmer than the evaporator if it's a really long pipe run. If the line's set, the liquid line and the suction line that you're running from the indoor to the outdoor unit are really long. And sometimes you got to add some refrigerant for that. Then once we go through the compressor, it's a superheated vapor, but because it got squeezed from this amount of volume inside a piston to this amount of volume, it really got hot. Pressure went way up, temperature goes way up. We almost go 4 times the amount of pressure between here to here. And the temperature goes up about 3 times. All right, so about 175 degrees coming out temperature-wise. And the first thing we got to do is de-superheat that vapor to get it to condense. Once it's fully condensed, about 3/4 of the way through the condenser, then we can subcool that liquid back down to feed it again all the way back through. All right, that's more realistic to what you will see in the book instead of tanks. But it's all the same thing. It's all the same thing except they're pipes, and we can run multiple pipes. Now, refrigeration is going to be a little different. So these are your temperatures, and what have I done? What's different about the metering device? This one has a bulb. So now again, this bulb is attached to like a hole like this inside here with a spring against it. So when this warms up, this is going to push more pressure down on that rod, which pushes the spring down, which is going to let more liquid feed through. Everything else is going to be the same, but now I have this that is able to control the amount of refrigerant, because now we're dealing with a refrigerator, a walk-in refrigerator. And when they have to have the food all loaded up right from the truck, and they've had the door open for like an hour or two while they unload all the food, then they're going to need all the refrigerant in the system. But in the middle of the night when the restaurant closes down and the cooks aren't going in and out of the restaurant walk-in cooler anymore, they just need to maintain temperature, and they're not going to need all the refrigerant in the system to maintain temperature. So this is going to adjust depending on the load, because the load's going to adjust throughout the day, depending on how many people are walking in and out of that walk-in refrigerator. Okay, now we're dealing with something real big. So we've changed the metering device into more of what you've been using on your trainers, and our temperatures are going to change too, because now we're not dealing with a 75-degree room, we're dealing with a 35-degree box. So if my temperature drops, what happens to this pressure on this side? What are you going to see on that gauge then? It's going to be lower. That's right. So my liquid, again, everything's normal, still feeding in, except my pressure is lower. Now I'm dealing with 50 psi instead of 69 psi. And now my temperature is also lower. And that means I have about a 10-degree difference between this box and this temperature of the saturation of the refrigerant. Now, go ahead and write this. This is all the stuff that we did, and we're broken down into groups. But you have your 4 basic components. Your compressor's number 1. It's normally where everybody starts. It's the heart. It's the most expensive part to replace, usually. And when they go bad, it's usually a time that maybe some customers think about replacing their unit. The whole unit ends up getting what ends up being a $2,000 to $3,000 part, ends up becoming a $15,000 job sometimes. And a lot of people don't have a lot of money even to replace the compressor at $2,000 or $3,000, or a credit card to get that. So asking them for $10,000, $15,000 for units even harder. The line that comes out of the compressor, the first one, is our discharge line. So if I have a whole unit outside, it's got the compressor feeding the discharge line right to the next component. They're all together. What is the next component? Condenser. That's right. And that's going to be our second component. And you said there were a couple different types of condensers, and we'll get into those in your slideshow from the group that had the condensers. And after we have all the stuff done in the condenser, what are we coming out with? What is coming out of the condenser? Liquid. So we're going to call that line the liquid line. They make it real easy. And that's where you're going to have your filter dryer, your sight glass, your receiver. Pretty much any of the accessories for the liquid line go on the liquid line. And then it feeds right into the next component after it's gone through the condenser and changed from a gas to a liquid and goes to the liquid line. That subcooled liquid feeds into the metering device. Now I can have an orifice, piston, what you saw in the first couple slides. I can have a TXV. I can have that electronic one that you talked about. There was like 2 or 3 others that we could talk about. And then they go from most of the time now from the metering device right to the evaporator, but there is an expansion line that they have, we call expansion tubes now. But they don't even mention them in any much, so we just go right from the evaporator, and then if it's getting kicked out of one side of the compressor, what's the other side of the compressor doing?
Sucking it in.
That's right, sucking it in, so we call that the suction line coming back, and that's where our superheated vapor. If it was R22, I would expect it to be 50 degrees or so, coming back to the compressor to be recompressed, all to repeat the cycle all over again. Now, again, you got one more thing to do with me on that paper. Don't draw this. This is how usually a lot of books have it though. They'll put the compressor, the condenser, and then they show you the rest, the meter device. The discharge line has the hot, high pressure gas coming out. As it goes through the condenser, it de-superheats, condenses, subcooled liquid feeds into the metering device. The metering device then takes that liquid, absorbs the heat, boils off to a gas, and the superheated gas goes back. What is this? Anybody? What is that? What is happening to the refrigerant? And why does it do this? Why doesn't it just go at a right angle up? What do they call this right here? Anybody know? If I put a straight line like that, what letter in the alphabet would that look like?
W.
Yeah.
U.
What?
U.
No.
I have a U right now.
Nope. If I put a straight line going like this.
Oh.
A D.
Nope.
A C.
A P.
P. P-trap. That's called a P-trap. In fact, there's one, if you take a look, on my condensate. Right there. And on some of those other units, there's a P-trap. If you look where the drain line comes out, there's one here on the refrigerant line. This is our oil trap. So you have oil returning back that flows. We want that oil that you put in the compressor. It's also mixing with the refrigerant and getting kicked out. And it's flowing with the refrigerant, and when it gets up against the pipe, they call that fouling. It creates a little bit of insulation between the pipe and the refrigerant, and we don't really want that. But it's got to do it because we need that oil in the compressor, and it's just with the refrigerant and the oil, they mesh so well together, so no chance for it to all stay there. Some comes out with the refrigerant, and eventually it collects here, and we want it to draw back up into the compressor when it first starts up. So it'll collect here, and then once that oil's all here and that compressor fires up and the refrigerant starts flowing, then it can get the oil back in the compressor, and you can see it in the sight glass right there if you look in the semi-hermetic. Alright, as long as you see oil in there, we're good. Now, this is how I want you to draw it though. You're going to draw a baseball diamond with the 4 basic components, and the pipes that connect them will be the baselines, and we're going to show half the system under high pressure and half the system under low pressure. So go ahead and draw a diamond on your paper, and I'm going to hand out some pencils to you, alright? You get a red and a blue, red and a blue, red and a blue. Nice. You can do it on the back. You take up half the paper. Nice, nice diamond. All right, everybody's got their pencil.
That's a nice rhombus.
Thank you. Hey, you know, hey,
One
squares
size.
aren't for everybody.
It's just a square that got
Oh, can I-
You want us to draw the squares?
What do you think I'm going to start out with for components? I didn't give you one. I gave you one right here. You don't have those?
My bad.
I mean, come on. You got to pick out your own.
No, I'm sorry.
All right, what component do you think I'm going to start with? Most important one.
Compressor.
That's right. That's our heart. So we're going to put our compressor at the home base. That's where we're always coming back to.
Do we draw that?
Yeah, well, you can draw it like just a regular circle like this. It's like a hermetic one. Because the one on your trainer, if I had to draw it, it would look something like a Pac-Man without the...
Pac-Man ghost.
It's a ghost.
It does look like a ghost. Yes, you are right. And then maybe if I squiggle the lines. So, but that's yours on that one. But this one doesn't have any bolts like this one, so I can't get into it. And this one's a suction cool compressor because it's got the suction valve on the end. I'll show you that a little bit later. So listen, what's the line coming out of the compressor then? What's my first baseline going to be?
Discharge.
That's right. So you go ahead, you write that discharge line, draw it with a red, kind of go light though, a light red, into what's first base? The condenser. So you're going to draw a squiggly, and you don't have to do the box with the fan, but do the squiggly line, right? Coming up like a coil, and then bring that up into what's the next line after the condenser? What do we make in the condenser? What did the condenser reject the heat and give us? Liquid. So yes, the liquid line feed into our metering device. And I like to draw the metering devices like an X. So if I was to draw that up there, I don't think I'd draw the fancy. I would just draw an X because it comes in, it restricts, and then comes out, in my opinion, when I draw it. But this line here is not listed in any of the books, but it's an expansion line. Because that's what happens. As soon as you come out, it's like if there were 10 of you in an elevator and the door opens up like this, and you guys got to come out together through, tightening up even, first thing you're going to do is expand once you get to the open area. And that's what happens with the refrigerant as soon as it leaves this orifice inside whatever device that we're using, whether it's just an orifice or a cap tube. Could be just a cap tube, and the length of the cap tube and the size of the hole in the cap tube is going to determine those molecules, how many of them go through from the high to the low side. And then after this evaporator absorbs all the heat that it needs to and boils off the gas, it should be nothing but superheated vapor. Boils off all the liquid to gas. It should be nothing but superheated vapor going back to the suction line, all to be redone at the compressor for compression to be kicked out of the discharge line. And if I had to divide down half this system with this going with a line from the top to the bottom, I could shade half of this lightly red because half of it's completely on the high side, and the other half I could shade blue because that's completely on the low side of the system. So that's what you should have. And that's how you should remember the refrigeration cycle when you're thinking about how it goes. Home plate, first condenser, second meter device, third. And if you can't remember that, if you could remember CCME, CC me? No. CCU? No. CC me. CC me. CCME. If you can remember the 4 letters CCME, you can remember compressor, condenser, metering device, evaporator. Compressor, condenser, metering device, evaporator. You got the 4 components. So then in your head, all you got to do is connect them up with the lines. And if you can remember the baseball diamond now, well, you know that the compressor and the condenser has a discharge line. And in between the condenser and the metering device, that's a liquid line. And in between the suction side of the evaporator and the compressor, that's our suction line. Because that's what's happening, it's coming back. And so if I had to put my hand on one of these, which one's going to be the hottest? Yes, but which one? Because I got two lines on the high side.
Liquid line?
Okay, liquid line is going to be the hottest.
Oh, it discharge.
The discharge.
The discharge, because it's the hot gas that's superheated coming out. And the liquid line is after it goes through the de-superheating, the condensing, and the subcooling. So it should be about 95 degrees, which would be hot. 100 degrees would be hot. To your body temperature, 105 even be a little hotter, but not as hot as 175, 165 coming out of here, which could burn you. And if you get it on a 95-degree day, it will blister your skin if you bump your arm against it and you're wearing short sleeves, especially down in Florida. Because in Florida, man, they get 110 degrees. Or you go out to Arizona, and they say it's a dry heat. And their units are different out there. They have a lot of evaporative coolers. They're using a completely different system than this cycle. But they have these cycles out there in Arizona because they do have rooms to need cooling. And if that gets 110 degrees outside, this line's going to get 210 degrees sometimes. It could go up to 300 degrees, which starts breaking down the oil. At 300 degrees, if this fan motor stops running and this whole system's been running for a day like that with the condenser fan motor inoperable, and nobody caught it, and that's why you're out there, and you touch this line first off, you are going to have a 3rd-degree burn. It'll give it to you. So you got to be very careful with this discharge line. It's got to be, should be wearing gloves and long sleeves, all the right stuff. And most of our service shirts are long sleeve shirts, but you could be working for yourself one day. So which of these lines would be the coldest then?
Suction.
Out of the ones that are listed here, the 3, yes, the suction line out of the 3 is coldest, but this is actually, it's a little bit cooler because by the time you get here, it's superheated vapor, and that was all 40-degree liquid with R22 feeding into it. So, but we don't have that line listed, but yes, you are right. The hottest line is the discharge. And then if I was to go even further and take a line and divide right here, everything above that line, what is up above that line? What state of matter would that be above the line? Liquid, that's right, because the liquid line's up here. And then everything below that line, what would the state of matter be? Everything's supposed to be vapor down here. Because if this compressor gets liquid, which is the whole purpose of this accumulator. The accumulator, I used to have it right here and I used to be able to grab it. I don't know where it went. But the accumulator, the word of the day today, is the piece of the device that acts like the receiver on that end that only feeds liquid to the metering device. We only want vapor going back to the compressor. Because if we get liquid inside the cylinder, it could damage the piston, the connecting rod could split, the wrist pin could shatter. There's a lot of pieces that can damage. The reed valve could snap or be bent, and it's not going to work. Blow a gasket. Something could happen internally to the compressor where it can run, but it ain't going to pump anymore. It's not going to work anymore to where we need the flow of refrigerant happening like it's supposed to happen. So we try and make sure that nothing but vapor goes through all our compressors and nothing but liquid can feed into the metering device. I do want to talk more with you about the different components. Now I can break it down to where there's 6 different types of compressors. There's a screw, there's a rotary, there's a scroll, there's a reciprocating, there's a centrifugal. There's 6 different types of metering devices. There's the floats, go on the high and the low side. You showed the electronic one. We talked about the cap tube already, the piston, and this one here is what? What do we call this one? A TXV. Very good. That's right. And then on our evaporators, right? Pretty much for a lot of these, they're what they call direct expansion. But in our chiller, we got one that's called a flooded. It's a little different. All right? So there's a couple different types of condensers as well. Water-cooled, air-cooled, and then evaporative cooled, which we don't really get into too much on our entry levels. But if you can get this down, this is a good stopping point for today. Because again, I'm going to break these components down even deeper with you, and we'll take it from there another day.